Section 5.7, Systems of Linear Inequalities. A system of linear inequalities is any time that you have two or more linear inequalities in the same variables, typically x and y, but it's similar to when we had a system of linear equations in two variables, which just was more than one equation. Just like a solution to a system of equations had to satisfy all of the equations, a solution to the system of linear inequalities must satisfy all of the inequalities in the system. In this particular example, we have the two inequalities, y is less than x plus 2, and y is greater than or equal to 2x minus 1. Basically what you do is you graph both inequalities in the same coordinate grid. You can see I have a solid boundary line for y is greater than or equal to 2x minus 1, and I have a dotted boundary line for y is less than x plus 2 because of the lack of or presence of or equal to in the inequality. And then you determine which section of the coordinate grid, either this area over here, this area here, this darker area, or this white area, that has all the points that satisfy both of these original two inequalities. And the way that it's worked out here, this dark region is actually going to be the collection of solutions to both inequalities. So for example, the point 0, 0, the origin, will satisfy both of these inequalities, as will everything else in that dark region. We're going to discuss how to find that next. When we need to graph a system of linear inequalities, we start by graphing each boundary in the same coordinate plane. I'm given two inequalities here. Y is less than or equal to 3, and y is greater than x plus 2. I have to first graph the boundary of y is less than or equal to 3, which is going to be a solid line because of the or equal to, and it's going to be a horizontal line that passes through y equals 3. The next line that I will graph is y equals to x plus 2, which will be a dashed line because of the just greater than inequality symbol. It will have a slope of 1 and a y-intercept of 2. So you can see here that I have my y-intercept of 2 and then a slope of up 1 over 1, rise over 1 of 1, which is my slope. Now that I have each boundary on here, I'm going to choose a test point from one of the regions created in the coordinate plane. You can see that there's this region over here. It's kind of the bottom right, the bottom left, the top left, and the top right. I'm going to pick just a point from one of those four regions, and hopefully I will end up getting a solution to the system. The easiest point to pick, if it's ever possible, is 0, 0, the origin, which in this case it is a possibility since it's on neither boundary line. I will start by testing the point 0, 0 in both of my inequalities. Now when I plug in 0 for y in the first inequality, I get 0 is less than or equal to 3, which is true. When I plug in 0, 0 into my other inequality, I get 0 is greater than 2, which is false. That means that 0, 0 is not a solution to the system of inequalities, and we're therefore not going to shade in that region, the bottom right region. So we guessed poorly, that's alright. We'll now just pick another test point in a different region. Maybe I'll pick one that's over here. I can pick any value that I want. I'll maybe pick this point right here, which we can see is the point negative 1, 2, 3, 4, 1. That's the point negative 4, 1. I'm just going to test that point in my two inequalities. I have no place to put an x, so I just worry about the y, and I test y. That gives me 1 is less than or equal to 3. That one works. I also do 1 is greater than negative 4 plus 2, which gives me 1 is greater than negative 2, which is true. Because negative 4, 1 is a solution to both inequalities in the system, it's a solution to the entire system, which means that every point in this region is also a solution to the entire system. Now I know which region will satisfy my system, so I just can shade in the entire region, either using a pencil or a highlighter or whatever to indicate that this is the region of all the solutions. It does extend forever and ever in this direction, and it does include this boundary line on the top, or at least that boundary ray. It does not include the points along the dashed line here. And that's how you graph a system of linear inequalities. Sometimes we are provided with a graph, and we can write a system of linear inequalities based on that graph. All we would have to do is establish the 2 or 3 or 4, however many boundary lines we have, write an inequality for each one of those, making sure that we have the correct direction and type of inequality symbol. For this, it seems that I have 2 different boundary lines, this dotted one and this solid one, with this dark shaded region being my collection of solutions. I'll start off with the easy one here, which is this vertical solid line. Because it's a vertical line, I know that I'm dealing with x being compared to a number. In this case, the number being -1. I'm going to leave the inequality out of it right now. I don't know which one I'm going to use yet, although I do know that it's going to be an or equal to because the line is solid. On the other boundary line, I can see that I have a y-intercept of -4 and a slope of 1 over 2. That's my rise over run. And so if I think about slope-intercept form, that's y, I normally would say equals, but this is going to be an inequality. My slope is 1/2. That's my m. X plus b is my y-intercept. In this case, that's -4. And I know that I'm going to have an inequality in there, but the inequality is not going to be an or equal to because this boundary line is dashed. Now in each of these cases, to figure out whether I want to be greater than or less than, I can just look at the graph. For this first boundary line, I've shaded everything to the right of it. In general, if I'm comparing something to x and I'm going to the right, I'm looking at something that's greater than the value that I'm starting with here. So going to the right, I'm going to say x is greater than or equal to -1. On my second boundary line, I've shaded everything that's above. And generally speaking, when I'm comparing something to y, going above also means going greater. If it was below, we would say less than, but in this case, because we're going above, we're going to say y is greater than 1/2 x minus 4. These 2 statements are my system of linear inequalities. I can pick any point that's within this dark shaded region and it will satisfy both inequalities here. Nice example would be the origin, 0, 0. If I plug 0 into my first inequality for the x, I get 0 is greater than or equal to -1, which is true. And if I plug 0, 0 into my second inequality, I have 0 is greater than 1/2 times 0 minus 4. Multiplying through, I get 0 is greater than 0 minus 4, which means 0 is greater than -4. Also true. Once again, the origin satisfies both of my inequalities and therefore is in the region that contains all of the solutions to the system of inequalities. Systems of linear inequalities can be used to solve a real-life problem. In this particular example, we're looking to schedule our fun for a vacation week because what says fun more than a schedule and systems of linear inequalities? And in this week, we have $24 to spend and we have 12 hours to occupy. We have a couple of options. We can buy a ticket to a 2-hour movie, and that could cost $8. We can also pay admission to a local bike path for $3, and that would give us the opportunity to ride for 4 hours. What we're going to do is we're going to use this information to write two inequalities and then graph them and kind of determine what the graph tells us about our options here in terms of spending time and money on this vacation. Like I usually do, I need to come up with variables to represent each of my options here. So I'm going to use X to represent a number of times that I'm going to the movies, and Y to represent the number of times that I'm going to the bike path, just because that's the order that they arrive in. It doesn't really make a difference there. To start off with this here, I'm going to think about spending the $24. That means that I can spend $8 for each time I go to the movies, that's 8x, and $3 for every time I go to the bike path, that's 3y, and in total I have to spend no more than $24, so that's going to be less than or equal to 24. Now in terms of occupying the time, the movie will last 2 hours, so that's going to be 2x. The bike path lasts 4 hours, that's 4y, and I only have 12 free hours, so that's going to be less than or equal to 12. Now that I have my two inequalities, I can actually graph these both on the coordinate grid that I have here. You can use slope-intercept form, or you can use the intercept method or any method to graph these lines. So here I have the graphs of the two boundary lines. That's just from graphing the lines using any of the methods we've discussed before. They're both solid because both of my original inequalities contain or equal to's in the original statements. Now I have to figure out where to shade. In order to figure that out, what I need to do is figure out the region, either this, 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 or this, that's going to contain all of the solutions to both inequalities. Once again, if it's an option, which it is here, I want to pick 0, 0. So when I test 0, 0 on both of my inequalities, I see pretty quickly that it's going to work out. It's going to make the first inequality 0 plus 0, which is indeed less than or equal to 24. And it's going to make the second inequality 0 plus 0 is less than or equal to 12. We probably expected that that was the case because we know that not going to any movies and not going to the bike path at all is technically an option based on it's not going to spend too much money and it's not going to take too long. Now that I know that the origin is one of our solutions, I know that this entire region in the bottom left-hand corner is going to be the collection of all of my solutions. And when I go to shade, I realize that I can actually limit my options a little bit more. First of all, I can't go to the bike path or to the movies a negative number of times, so I'm not going to leave the first quadrant. I also really only have a handful of actual opportunities. I'm not going to go to 1.5 movies, so I really have everything that's at these locations here, right on the grid, as true options for what I could do. I could go to, say, 1 movie and 2 trips to the bike path. I would be able to have enough money and time to do that. These are really my 9 legitimate options. I guess I missed one up here. I guess I could just go to the movies 3 times, or I could go to the bike path 3 times, and I'd have either money or time left over depending on the circumstance. But those are my options there. And that's how you use a system of linear inequalities to solve a real-life problem.